So hello everyone, and welcome back to the channel. The title of this video is React Native Skia and Trigonometry, my take. And what we're going to do is we're going to go through a series of sort of mini lessons that will eventually build up to building the really cool demo you see off to the side. So the question is, why call this my take, right? And the reason is because a lot of this is common knowledge. For example, if you've taken pre-calculus, you already know how a lot of this trigonometry stuff works. Not only that, but even on the React Native side, William Candillon has his own video called Beautiful Trigonometry that explains a lot of this as well. The thing is, I found myself reviewing trigonometry every year and having to go through the same exercises every single year in order to remember how to do it. So I thought it'd be great if I made a little resource that explained my refresh exercises, and I'm hoping that maybe it'll help other people as well, either learn this for the first time, or if you already know how trigonometry works, give you a good set of exercises that you can use to kind of review the subject year after year like I do. When I was learning how to program, I really liked an author called Zed Shah, and in his books, I can't remember the exact quote, but it was something along the lines of the fact that sometimes when you learn something new in programming, it's not enough to have something explained to you one way. Sometimes that way isn't the way that's going to click with your learning style. And so I'm hoping that if I give a little bit of variety to this topic, maybe I'll be able to help some people learn trigonometry and React Native Skia that wouldn't have necessarily been able to learn it otherwise. Anyway, if nothing else, I had a lot of fun relearning this and a lot of fun making it, so I hope you guys enjoyed this video as well. Alright, let's get started. So part 1 is going to explain how we can actually draw circles on the Skia canvas. And what we're going to do here is we're going to get into the mathematical foundations behind it. However, before we can truly understand how circles work, we first have to understand triangles. And I know it seems maybe a little bit counterintuitive, but I promise you after this section, it will make sense. And of course, the type of triangle that we really need to understand is right angle triangles. And let's quickly talk about the anatomy of a right angle triangle. So of course, there's the right angle part, which is this corner here. And there's also the angle opposite of the right angle side, and we will call this angle theta. There's a few other important parts of triangles as well. There's of course the hypotenuse, which is the long side of the right angle triangle. There's the opposite, which is the opposite side between that and the theta. Finally, there is the adjacent side, which is the side that's on the same side as the angle. When we use triangles, there's 3 different ratios that probably you've heard about before, but just in case, I will review them. First one is sine, and sine is equal to the opposite over the hypotenuse. There's cosine, which is equal to the adjacent over the hypotenuse. And finally, there's tangent, which is equal to opposite over adjacent. So let's zoom out here now that we have this model. And you can see that, our triangle is kind of suspended in space there. So what if we drew a nice Cartesian plane here? And let me quickly get our functions here out of the way, so we can make this line a little longer. And let me grab one more line. Okay, so now that we have this Cartesian plane, the next thing that we're going to do is we can actually draw a nice, neat circle around this. And this is going to be important to understanding this whole thing in just a second. Okay, so you can see on our triangle that there are different points here. And of course, you're going to see that one point is along the edge of the circle. One point here is at the center point in the Cartesian plane, where this is the y-axis, and this is the x-axis. And finally, we have one point right here along the x-axis. So something interesting that you can observe here is that if you take the hypotenuse and you take its length and you sort of extend it to just any part on the circle, anywhere, even like on this side or something, for example, you will always end up with a right angle triangle. So basically, I could extend this down. Oops, picked the wrong thing. So you can extend this down, and you'll get another right angle triangle here. And this rule, of course, sort of holds for basically everywhere else in this entire circle. Keeping this in mind, right? Instead of hypotenuse, opposite, and adjacent, maybe we could give these different names that are better indicators of what these are in terms of when you work with a circle. So it's better in our case to call this the radius, and we can call this side x, because it goes along the x-axis, and this one y because it goes up and down along the y-axis. And I'll explain why that's the case. So there's kind of two coordinate systems at play here, and I might have made them obvious, I might not have, but let me make it explicit here. The first is Cartesian coordinates. And these are just your normal xy coordinates, like you might see like up here, right? You can express it as x and y. But there's another type of coordinates here called polar coordinates, and this is often used for circles. And these are represented by the radius and an angle theta. And that makes sense, right? Because if you have an angle and you know how long the radius is, you could really represent just about any point on this circle. What we have to do is we can do a lot of our math for circles in polar coordinates because it's much simpler, but then we always have to map our polar coordinates back to Cartesian coordinates so that we can draw them in Skia. So the way we do this, if we zoom in, now that we've changed everything around, we've changed the names, I apologize. You could say that sine theta is equal to, instead of opposite over hypotenuse, you would now say that it's equal to the y over the radius. And then if we rearrange that, what you end up with is radius times sine theta equals y. We can use this function here to give us our y coordinate. And we could also say cosine theta is equal to x over radius. And if we rearrange that, you get r times cosine theta equals x. So now we can use these two functions to do a conversion between our polar coordinates and our Cartesian coordinates that we had shown earlier. So the last thing we want to talk about here is how do we actually get all the points of the circle? Like, it's fine that we have these nice mathematical functions or whatever, but how do we draw the whole circle? And of course you're going to see it in code in a minute, but in the circle, half of the circle is of course called the radius. You know, I showed these lines here, how they can kind of be drawn from any arbitrary point. Another thing that we know is that if we drew every possible line, that would give us every single point that could possibly be in the circle. So the range of all these possible points is 2 times pi. And the reason we use pi is because we're measuring our angles in radians here, we're not measuring them degrees. When we use radians, it actually makes the math a lot easier to compute when you use polar coordinates. And so basically, what that gives you is that you can say for every single angle from 0 to 2 times pi, you'd want to plug in all of these angles into these two functions, and that will give you every single possible combinations of angles that you need to use in order to create the circle. So let's jump over to code now, and I'm going to prove to you that's possible in code. So now that we've gone over the conceptual basis of how circles are made and all the mathematics behind how we can create one, what I'm going to do is I'm actually just going to code out a circle from a path, and I'll start by answering the obvious question, can't you just use the circle that's built into React Native Skia? The answer is yes, you can and should be using that circle. That's the better version of it. However, I want to code it out as a path first. And the reason is because it's hard to understand the rest of the chapters of this without first understanding how circles work. So the exercise of actually going through and coding the circle itself is very helpful to understanding everything that comes after. Okay, so using the math that we saw earlier, let me create a couple constants. The first is going to be the radius. And I'll make that easy. That's just going to be 100. Next, I'm going to make another constant, and I'm going to call it full rotation. And that's going to be equal to times math.pi. Whoops. Because as we said earlier, in the earlier explanation, 2 times math.pi is all the angles in the full rotation of a circle. So I'm going to create a path using use path value. And I know this is a little bit overkill for what we're doing, technically. However, it's just a little more convenient to make paths this way. You can optimize if you want later. So to get all the angles, what we're going to do is we're going to go from 0 to a full rotation. And then we're going to do I++. And things are going to be a little bit broken when we're done, but I'll come back and I'll fix them and I'll show you why there's issues. Okay, but what we're going to do is we're going to first get x. And as we discussed earlier when we were doing the conceptual explanation, x is always equal to the radius times math.cosine and I. And the reason we use I is because I is the current angle that you're at. And then for y, we do something similar, just with sine, as we discussed. Now we have a little bit of language specific stuff to do. We have to say that if I is equal to 0, then we're going to take the new path and we're going to move to x and y, because that's where we want to start the drawing. Otherwise, we're going to line to x and y. And then the last thing we're going to do once the for loop is done is close the path. Okay, so clearly nothing's showing yet. And the reason is because we have not put our path in the canvas. So let's do that. And we're going to make its style to be the stroke style. The color is going to be a terminal green color that I made below that I thought was kind of nice. And the stroke width is going to be 10, I guess. So as you can see, the circle is kind of weirdly out in the corner. This is easy to fix. All you do is you add an offset, and the offset just kind of shifts the formula down to the starting point that you want. So in this case, we're going to do width divided by 2, because that's the middle of the screen horizontally. And then to center it vertically, we just divide height by 2. And now you see that the circle is extremely lopsided and kind of choppy. The reason is because there's not enough samples here. So if we say I plus equals 0.01, the circle will be rounded because there's more points. If I increase this number so that you have less points, you kind of see that as there's less samples or less and less, the circle starts to get gradually more and more choppy. So that's why you need more samples just to make it more round like that. Anyway, that's how you code out the circle. Let's now move on to talking about how gestures work with circles. All right, so now that we understand how circles work, the next thing we want to do is talk about how we can get sort of the round gesture effect. And what that is when you have a dot like this, and the user is able to use their finger to sort of trace around a circle in this type of way. However, normally, when the user does some sort of gesture, they don't just touch the edge of the circle, they're often kind of a little inside or a little outside. And we can compensate for that pretty easily. So let me quickly give a little line here. And then let me fill this in a little bit. So let's say this is the point that we want the user to be at. And then this is the point that they actually touched out here. So what you'll notice right away is that the angle between the x-axis here never really changes. The user can go out to like a pretty wild distance and the angle will always stay the same. And this is great because it means we can use our trig ratios in order to determine what theta is. And then once we have theta, because we define the radius ourselves, which is the size of the circle, we can then just use our normal conversion functions to convert it back to Cartesian coordinates that we can use. So let's start by computing this theta. And in order to do that, what we need is a ratio called arctangent. And that's normally y over x. Things are a little different when we do this with computers. We use a function called arctangent2. And the reason is because we can pass in y information, and that allows us to basically know what quadrant you're in. If you don't do that, you end up getting kind of stuck on this side of the y-axis here, and that's not what we want. We want to be able to circle around here wherever we desire. But how do we get the x and y that we can use here, right, to get the theta that we want? And the way that we do that is we subtract this value. So let's call this the outer x and the outer y. And then I'm going to have this point, and I'll call this the inner x and the inner y. And so we can say x prime is equal to the outer x minus the inner x. And then y prime is going to be equal to the outer y minus the inner y. So once we have those values, what we do is we plug them into our arctangent 2 function. Or it's the opposite. It's y and x. And then that will give us back the angle. And once we have the angle, we can then get this value here by just using those same functions that we declared earlier. So x is cosine theta, which is this theta, and y is equal to r times sine theta, which is of course this theta again as well, and that will give us this point here. All right, so let's go into code and I'll show you that this works as I described. So now that we've seen how gestures work sort of conceptually, I thought I would then code out a basic round gesture, kind of like what we just described. So right now I have everything static. Like if I try to click on this circle and drag, nothing happens. And I want to also kind of introduce our boilerplate too. So I just have a very basic text here. I have this tiny circle and I have this larger circle, but nothing's really hooked up. Like we're not using gestures. We don't have any math going on, nothing like that. I did store the values, like the initial positions of everything inside of shared values. But right now that step kind of has no significance. So let's do what we said earlier and let's create the gesture. And of course, the first step to that is wrapping everything with a gesture detector and then creating a gesture. And I'll give that to our detector here. Okay, so what we're going to do now is we're going to set the onChange value. And we're going to grab the x and the y from this. Now inside of here, what we're going to do is we're first going to calculate the values of x and y prime. And as you remember from earlier, if our finger is outside of the circle, that's kind of the outer value, and then the inner value is what's the center point here. And so we know that the center point is height divided by 2 and width divided by 2 because the circle is perfectly in the middle of the screen. So let's calculate these now. So y prime is equal to y minus height divided by 2. X prime is equal to x minus width divided by 2. Okay, now we can use arctangent 2 like we described earlier. And we'll call that our theta. And inside of here, what we're going to do is we're going to give it y prime, then x prime, and finally, we're going to calculate the position of everything. And so we're going to say x position is going to be equal to the radius multiplied by math.cosine times theta. And then we have to add back the width divided by 2 so that we can offset everything. Oops, and that should be dot value. And then the y position dot value is going to be kind of similar. And this is sine, and this is the height. Okay, so at this point, we're almost there, and we can actually move this around the circle if we like, which is really cool. But normally, when you have some kind of like a sort of circular indicator like this, you often want to get some information out of it in order to display it. And so let me show you how to do that now. We have this value radians here. Let's just display the number of radians up top. And so that's not so difficult. We'll make a variable, we'll call it distance. And we're going to make it negative theta. The reason is because normally on the Cartesian plane, values go from 0 in the bottom left-hand corner to higher values at the top. On computer devices, for whatever reason, it's kind of the opposite. 0, 0 is up here instead of down here. Things are kind of inverted, so we have to adjust for that. Next thing we have to say is, if the distance is less than 0, we need to make an adjustment to the calculation. And we have to take the full rotation and subtract the theta value from that. Finally, we take our radians value and we make it equal to the distance. So I want to zoom in on why this part has to happen here. Like, why, if the distance is less than 0, do we do this calculation? The reason is because arctangent 2 can only give us a set of values between 0 and math.pi, and that sort of flips when you get past half. So in order to adjust for that, you have to do this little calculation to make sure the value always goes up. So if we reload, oh, we don't see the text because I never used this value. Let me quickly plug it into the text here. All right, let's try this again. And as you can see, the number of radians displays as we go along. And you can see at the halfway point, that's 3.14. That's about 1 pi. And we should be able to get this value around double that here. And we can. So we know that this is circling around and it's giving us an accurate number of radians. If you wanted to have this be like a percentage indicator or something like that, you could always divide the progress around the circle by the total number of radians. But regardless, that is a circle gesture. Let's move on and work on some nice polar curves. Okay, for this last section, what we're going to do is we're going to talk about polar curves and how you can do all the math for those so that we can add those in code just a little bit later. Basically, you'll see these two little blobs here that I have, and this is just information from Wikipedia. It's a great place to find polar curves and lots of kind of simple math stuff, which is really nice. And you'll see in this first little blurb here, we have some important information, which is that a rose is a set of coordinates that are specified by the polar equation, which is alpha multiplied by cosine and then k multiplied by theta within that. So let me kind of pull this apart a little bit just to make it a little more understandable. So r is our radius, alpha is the size that we want, and k is the ratio. And whatever the ratios are that are specified by the rose itself, which is the polar equation that we're using here, is going to be the ratio that we adopt. So you'll see off to the side here, it tells us that the 8 petals of the rose have a k value of 4/5, and that we have to loop 10 revolutions in order to go through this whole thing. So if we were to fill out this formula, let's say we wanted our size to be 100. So this would be r equals 100 multiplied by cosine, and then you'd then multiply cosine by 4/5 times whatever theta you pass in. So you'll notice we have theta, we have radius. These are, of course, polar coordinates. And what that means is that once you're finished this, what you're going to have to do is you're going to have to map this back to Cartesian coordinates. And of course, we know how to do that. So once we have that value, all you would do is you would say that the new x value would be equal to the radius you just calculated up top, multiplied by cosine times theta, and then you just add any offset if you wanted to, push it down or push it to the left or whatever. Same thing's true for y. Y times sine theta would then convert this radius back to what we could use in Cartesian coordinates. So as you can see, this is actually pretty elegant, and from a mathematical perspective, pretty easy to do and pretty easy to just understand based on everything we've done so far. And I think it'll be cool to see this in code. So let's jump over there and let's do that right now. So now that we understand how polar curves kind of work, and more specifically how roses as a type of polar curves work, I have a new example for us to work through, and we're just going to code through and make an actual rose. So I do have some boilerplate for us like usual, but again, it's stuff you already know how to do. So this circle down here, that's what we coded out in part 1. The ability to have things sort of stick around the circle is what we did in part 2. And for part 3, we're actually going to draw the rose where this line is right now. So actually, I'll just collapse these because they're not going to come into play as we work. And the last thing I just want you to keep in mind is that this total rotations value, this shared value, is what we're going to use to time everything. I'm going to comment it out for now though, just because I don't want things to be spinning as I'm kind of working through this. It's a little bit distracting. So let's get started by creating our rose function, and we'll call this getRosePoint. This is going to take in a theta, which is a number, and return a point. And so in order to do this, we actually have to offset the rows, and this works just like any other circle, but we're just going to compute it a little bit beforehand. And we're going to just keep it in the middle, so we're going to keep the center offset. Our y offset is going to be the height divided by 2 minus 150. This just means that from the middle of the screen, which is offset at height divided by 2, we're going to pull it up 150 points. That's not a big deal. Next, we're going to put our ratio here, which is the value of k, like we specified in the earlier description. And then what we're going to do is we're going to calculate our new radius. And that's going to be our radius constant, which is 100, multiplied by math.cosine theta. And actually, we have to multiply k by that theta. Whoops. Okay, and that gives us the radius that we want. Next, we need to calculate the x position and the y position. And we can do this using the usual suspects of radius times math.cosine theta to give us the y, plus the offset x. And the y position is radius times math.sine theta plus the offset y. And we're going to return x is the x position and y is the y position. So quickly before we move on, I'm going to mark this as a worklet so the app doesn't crash later. And now what we're going to do is we're going to create the empty path. And this path is kind of that placeholder in the background that you saw for the rows. And yeah, let's make that now. And that's going to be a use path value. And we also have to make this a worklet. Okay, with that boilerplate out of the way, things pretty much work the same way as they do for a circle at this point. We just say let I equal 0, while I is less than the row's full rotation this time. We do I plus equals 0.1. And the row's rotation just matches what we had from Wikipedia, which is that the full rotation is 10 pi. So 2 times pi times 10 is what we need. And finally, we get every point by looping through and getting all points from I is equal to 0 to the max level. Again, exactly like the circle, if I is 0, we will move to that point. Otherwise, what we're going to do is we're going to line to that point. Okay, so let's draw this in and let's see if it worked. And we're going to do that up here. And path equals empty path. The color is going to be equal to my 5th color. The style is going to be equal to stroke. The stroke width is going to be 3. And the opacity is going to be 0.2, so that looks kind of faded in the background. And if we have a look, you can see that it is there, and it is that nice faded color that we want. Next thing that we want to do here is that we want to actually get this rose to start rotating in the same rhythm with the circle. And the way we do that is we start by making origin, and the origin is the point that we want to rotate around, which would be the middle of this rose. And what that would be is a vec, and you need this because Skia requires it. And that's going to be width divided by 2 and height divided by 2, subtract 150. And this is the same sort of calculation that we did here in the get rows point. Similar to the offsets, that's exactly what we want for the middle, which is the origin. So next thing that we're going to do is that we're going to create a transform value. And that's going to be the value that actually rotates it. And this is going to be a derived value. And the derived value is going to change based on the total rotations. And here we're going to return rotate z. And its value is going to be the negative total rotations dot value. And then we are going to do 5/4. The reason we have to do these 5/4 instead of 4/5 and negative is because this is rotating sort of the opposite direction as the path that's being filled. So it has to be an inverted value. Finally, what we need to do is we need to take our group, set the origin to the origin we just created, set the transform to this transform. And initially you're going to see nothing, but if I turn on the animation, you'll see that these two are turning in sync, which is pretty cool. The last thing we need to do is actually fill out the path. All right, so for the last step with the filled path, things are almost the same as the empty path. So I can kind of copy paste this. There's probably a good way to deduplicate this, but for the sake of teaching, I don't really mind duplicating it. Basically, all the code is the same. The only difference is you want to always be less than the total rotations dot value, and we want to multiply that by 5/4, which is the same inversion that we did with the rotation earlier. Now, if we take this path and we put it here, and we make the opacity 1, whoops. So far we have nothing, but as soon as I activate the use effect, oh, let's reload. As soon as I activate the use effect, you see that everything fills in along with the exact same cadence as the circle is going around. All right, so that's everything, guys. Thank you for watching today. And as always, happy hacking.